implement the concept of GAN using the facilities provided in KERAS. But this is the agenda of my presentation. As you know, machine learning is the subfield of AI which specializes in teaching a machine through its prior experience. I think Dr. Judy yesterday explained all the basic concepts of machine learning and all. And as you know, machine learning is nothing but it is the ability of machines to automatically learn without being explicitly programmed. Here, in the first definition, the machine learning is the subfield of AI which specializes in machine teaching a machine through its prior experience. Prior experience is very important, and in computer science, this prior experience is nothing but the data set available in our hand. And the origin of machine learning can be traced back to 1957 when the concept of perceptron model was introduced. And because the perceptron model, the concept of perceptron model was introduced in 1957, that is actually introduced by Rosenbold. And after that, a drastic change we can see in the area of machine learning. And again, as you know, perceptron can be considered as a device or a concept that makes decisions by weighing up evidence, and this is very important, weighing up evidence. And when we move on to the artificial structure of a neuron, neuron, and these are the various components included in the architecture. That is here that configuration is called a perceptron. And when we look onto that particular construct, we can see some inputs, that is x1, x2, x3, etc., xn, together with weights w1, w2, w3, etc., wn. And these inputs and weights are real numbers and can be positive or negative, whatever it may be. And again, when we look into the figure, we can see some components available in that particular construct, and these components are nothing but weights, summation processor. Summation processor is actually, this is the summation processor, and an activation function. These are the three very important components of a perceptron model: weights, summation processor, and activation function. And here each input that is individually weighted, and these weights actually represents the significance of these inputs, because all the inputs are not equally significant. And here w1, w2, w3, or w1 represents the weight associated with the first input x1, w2 the weight associated with the second input x2, and so on. So each input is individually weighted. And when we consider the case of summation processor actually computes the quantity w1 x1 plus w2 x2 plus etc. plus wn xn. And this information is fed to the activation function. That means inside the activation function, w1 x1 plus w2 x2 plus etc. plus wn xn becomes the input. And based on the selection of the activation function, we can generate an output corresponding to that particular input, and the input is nothing but w1 x1 plus w2 x2 plus etc. plus wn xn. So here when we consider that particular operation, here all the inputs are individually weighted, added together, and passed to the activation function. And the simplest activation function, and that is a step function. I think all of you know what is the working of a step function. That is outputs a1 if the input is greater than a particular threshold, and otherwise its output will be 0. That means when the w1 x1 plus w2 x2 plus etc. plus wn xn is greater than a threshold value, we can say that perceptron has fired. Otherwise, there is no change in the output in that perceptron model. Therefore, its output will be 0. Okay. And this is the case with the activation function, that is the step function. Some other activation functions are also available, and such as sigmoid, then softmax, tanH, relu, leaky relu, etc. A number of other activation functions are also available. KEDAS. Then this is the concept of a single neuron. This is the concept of a single neuron. That is, when we talk about the concept of a single neuron, inside that single processor, and an activation function is there, and it is the responsibility of that activation function to generate the output. Next, we can move on to the multi-layered neural network. But here, an MLP is composed of one input layer, one or more hidden layers, and one final layer, and two or three two or more or one or more hidden layers are there, and a final layer is there, and that final layer is known as the output layer. And when an artificial neural network has two or more hidden layers, and that construct can be considered as the deep neural network, or in short DNN, and that is the concept, or that is the idea behind the concept of a deep neural network. That is, in a deep neural network, we always expect two or more hidden layers. And when we consider the information flow in a deep neural network, and this is the information flow, that is from input layer, the information flows to the hidden layer, then from hidden layers, it goes to the output layer. And in an MLP, usually we expect multiple hidden layers. Each layer may contain any number of nodes. Any number of nodes we can expect in a particular layer. And the number of classes actually determines the number of nodes in the output layer. Then how many nodes in the output layer, and that is actually determined by the number of classes in the classification problem, for example. Okay. And in order to work with a deep neural network, we have to understand the concept of a learning algorithm, and what type of a learning algorithm is used in a multi-layer perceptron. And it is the responsibility of the learning algorithm to tune the weights between the output layer and the hidden layer. As I said, in the case of the single perceptron, and in the case of single perceptron, all the inputs are individually weighted. So here, in the case of a multi-layer perceptron, we expect some weight matrices in between the various layers. In between the various layers, we always expect some weight matrices. So tune the weights between the output layer and the hidden layer, and that is the functionality, first functionality of the learning algorithm in MLP. Then after that, we can tune the weights between the hidden layer and the input layer. That means this type of a flow we always expect in the case of multi-layer perceptron. So learning algorithm in multi-layer perceptron tune the weights between the output layer and the hidden layer. Then after that, we can tune the weights between the hidden layer and the next hidden layer, then that hidden layer and the next hidden layer, and so on. And at last, the weights between the hidden layer and the input layer. And these type of a processing we can always expect in the case of a multi-layer perceptron. And in order to tune the weights, the method followed is take the error at the output layer. That means, as I said earlier, there is always a forward propagation step. And as a result of that forward propagation step, in the output layer, we get an output. That is the predicted output. And the actual output that is available in our hand. And we can compare the difference between, or we can compute the difference between the actual input and the predicted input. And that is actually known as the error. So we can compute the error at the output layer. And using gradient descent, we can proportionally propagate this error backwards to tune the weights. And that is the methodology we always follow for tune the weights between these layers. That means, and that concept is actually known as the training in multi-layer perceptron. That is, tune the weights. The process of tuning the weights or optimizing the weights between the different layers of a network is actually known as learning in a multi-layer perceptron. And this is the simple architecture of a multi-layer perceptron. this is the input layer, and here this is the output layer, sorry, hidden layer, and this is the output layer, and in the output layer we can expect the decisions, and if the problem is a 3-class problem, in the output layer we can expect 3 different neurons, and these are the 3 different neurons. Okay. And when a deep neural network has used in image classification, and what is happening in each layer, and that is represented in this diagram. Here in the input layer, we can provide the required input to that particular network. And in the first hidden layer, some low-level features are extracted from that image. From low-level features are extracted from that image. And here, in the case of a deep neural network, in the input layer, the input is nothing but the pixel intensities of this particular image, and that is the input to this input available in this input layer. And from that pixel intensities, as a first step of the process, we can extract some low-level features. For example, edges or straight lines, etc. These are the low-level features we can extract from the input image, and that is the that type of an low-level feature extraction is going on in the first hidden layer. Then when we move on to the second hidden layer, features obtained from the first hidden layer can be combined together to generate more abstract features representing that particular image. Okay, then when we move on to the third hidden layer, the features obtained from the previous layers can be again combined together to generate more abstract features, and this process is continued until we classify the different objects contained in the image, and that classification actually happens in the output layer. Okay, and this is what is actually happening inside a multi-layer perceptron or a deep neural network. Then, as I said earlier, training in multi-layer perceptrons, that is very important, and these are the various stages happening at the time of training a multi-layer perceptron. For example, for each training instance, that means for a particular image, for each training instance, the back propagation algorithm, and that is the algorithm used in multi-layer perceptron for training the network, back propagation algorithm, first makes a prediction, and that is forward pass. Then from that prediction we can measure the error, because actual value of that particular class is available in our hand, and that is the actual decision, and that is the prediction and actual decision, and the difference is called the error. That is we can measure the error, then goes through in each layer in reverse to measure the error contribution from each connection. That means in each hidden layer, by considering this error, we can compute the total error contribution in each hidden layers, and finally slightly modify the connection weights to reduce the error. To reduce the error means in the next pass, in order to reduce the error, we actually modify the weight values, and for modifying these weight values, we actually use the gradient descent method. That is this step is actually known as gradient descent step, and I think all of you know what is the concept of gradient descent, or gradient, dy by dx, that is the derivative of y with respect to x, and in this case we use dw by de. De means that is the derivative of the weight with respect to error. Okay, and with the help of this gradient descent step, we can modify, or we can tune the weights. And as you know, an MLP or the deep neural network or the multi-layer perceptron is often used for classification. And when the classes are exclusive, that is example, for example, classes 0 through 9, in the case of handwritten digit image classification. the output layer is modified by replacing the individual activation functions by a shared softmax function. Softmax, and that is a very important activation function always used with the classification problems. If the classes are if we have two or more different classes are there, in that case we always use the softmax function as the activation function. And this is the mathematical format of that softmax function. Softmax of Zi is equal to e raised to Zi divided by sigma over j e raised to Zj, where Z is the vector containing the scores of each class for the instance X. That is, when we input an instance, and that instance is a part of a 10 class problem, then corresponding to that particular instance, we expect 10 different scores. 10 different scores. That means as an output, we get a vector, and in that vector, 10 different informations are there. And first information, that is the amount of the result, amount of the classification result corresponding to the first class. And the second component is nothing but the information corresponding to the second class, third class, and so on. So Z is the vector containing the scores of each class for the instance X, and softmax of Zi. That is the estimated probability. So softmax of Zi provides or gives a probability, and that the instance X belongs to class I, given the scores of each class for that instance. That means the scores are available in Z. Then by considering that these scores, we can compute a probability corresponding to the ith class using this softmax function. So this softmax function actually provides a normalized value, and that is a probability value. That is a probability value computed from the individual scores. Okay, and this probability value tell you the chances of having that particular decision corresponding to the class. Okay, but here this is the architecture by incorporating the softmax activation function in the classification problem. The input layer, and here we have only two inputs. Then this is the first hidden layer. Then in between the hidden layer and the output layer, we can expect any number of layers, any number of hidden layers. And this is the output layer. And inside that output layer, if the problem is a 3-class problem, in the output layer, we can expect 3 different neurons. And inside these neurons, we can compute these scores corresponding to each class. This is the this neuron is responsible for computing the score corresponding to the first class. This neuron is responsible for computing the score corresponding to the second class, and this neuron is responsible for computing the score corresponding to the third class. And these scores are passed to the softmax function. Then as a result, this softmax function provides some probability values. For example, this is 0.8 and this is 0.1 and this is 0.1, for example. Then since the first probability is high, and in that case, this particular input is mapped onto the first class. And that type of a processing is actually happening inside the multi-layer perceptron or inside the deep neural network. And in the case of a softmax function, the output of each neuron corresponds to the estimated probability of the corresponding class, as I said earlier. And this architecture is an example of a feed-forward neural network, or FNN, or we can simply call it as a deep neural network. And an MLP contains 2 or more hidden layers. Then such an MLP is called the deep neural network, or DNN, and this is the architecture of such a neural network. There is a deep neural network. This is the input layer, hidden layer 1, hidden layer 2, hidden layer 3. Then we can expect another layer, hidden layer 4. Then at last we have the output layer. And then my next task is how we can build a deep neural network, because the architecture of a deep neural network is very essential in GAN. Okay, and in order to explain the concept of the architecture of a deep neural network, we can consider a very simple example. consider this fashion MNIST data set, and this fashion MNIST data set is an experimental data set available in Keras. This data set actually contains 70K images, and all the images are of 28 by 28 in size, and these are grayscale images. Actually, this is a 10 class problem. 10 different classes are there, and these are the various classes of the images contained in the fashion MNIST data set, and these are the images. Here, the classes are t-shirt, trouser, then pullover, etc., etc. 10 different classes are there. Then, in order to implement that particular concept, we need some libraries, because a number of different dedicated functionalities are there, and these functionalities are available as various libraries, and these are the libraries. I don't like to discuss more about these libraries, because I think all of you are familiar with all these libraries. That is import numpy as MP, and that is in order to use various metrics operations. We need a number of different methods are there for processing the information contained in the metrics, and all these functionalities we can access with the help of an object generated with the help of this numpy. That is numpy array. Okay, but here with the help of this object we can access all the functionalities, and in order to display the images, we need some other functionalities. That is import matplotlib dot pyplot splt. That is we can display all these images, we can visualize the images, and all these operations can be done inside a particular deep learning program with the help of another functionality, and that functionality is known as matplotlib. Then import TensorFlow STF, and TensorFlow means a high dimensional vector, which can be considered as a high dimensional vector, and all the different operations associated with a high dimensional vector or tensor can also be done with some specialized methods, and all these methods are part of the TensorFlow. Then again, inside the TensorFlow, we have another very important functionality, and that functionality is actually known as Keras, and this provides all the necessary facilities for generating deep neural networks, then convolutional neural networks, etc., etc. A number of different basic functionalities are there, and these functionalities are actually part of this library, and the library is known as Keras. That is very important. Then next is np.random.seed42. That is in order to initialize the matrices we are considered for implementing this activity, and that type of an initialization or the values contained in the matrix we have to initialize, and that initialization process is actually done with the help of a random number generating function, and this random number generating function can be available inside the numpy array, and we can access that function with the help of np.random.seed42, and in order to reproduce the initial values, we can call this function with the help of a seed value. Then similarly, in order to initialize the TensorFlow or the high dimensional matrices, we use another functionality, and that functionality is tf.setRandomSeed42, and this is for initializing the tensors, and this is for initializing the matrices. Then in order to implement that activity as a first step of the process, we have to load the data into our program, and as I said earlier, this fashion MNIST, and that is actually a part of the Keras library, and from the Keras datasets we can load the fashion MNIST with the help of this particular statement, the keras.datasets.fashion MNIST. And for that, in order to store that, we can create an object, and this is the name of that object, or fashion MNIST. Okay. Then in order to train the model developed as a part of this particular experiment, we have to create the training data set, then test data set, and so on. I think all of you are familiar with training, testing, etc., etc. And the training data and test data can be created directly with the help of the functionalities available already available in the Keras. And for that, we can make use of a dedicated method, and that method can be accessed with the help of this particular object, that is fashion mnis dot load data. So with the help of this load data, we can create the training data, that is X train, Y train, test data, that is X test, Y test. That means when we use this load data, around 70% of the images are mapped onto the training data, and the remaining objects are mapped onto the test data. Then after loading the or creating the training data and test data, for example, we can just visualize the size of the training data set and size of the test data set. And for that, we can make use of print xtrain.shape, then x.shape. Okay, but here 60,000 images are, and all the images are of 28 by 28. And all these 60,000 images are now available in the training data set, and the remaining 10,000 images are available in the test data set. And this is a normalization function. X train is equal to X train divided by 255.5, because I already mentioned that this data set contains some grayscale images. And in a grayscale image, the intensity of the various pixels of that image varies from 0 to 255. So, with the help of this particular expression, we can normalize the intensity values, and as a result, we can transform all these intensities values, that is 0 to 255, can be mapped onto a small domain, and that domain is actually 0 to 1. That is, all the pixel intensities can be mapped onto 0 to 1 with the help of this normalization. So, X train, that is X values of the training data set, and Y train is the label. Y train train actually contains the corresponding labels. So all the pixel images, pixel intensities of the images are now transformed to a small domain, and that domain is 0 to 1 domain. Okay, similarly, the test data can also be normalized in that way. Then after this normalization, suppose we want to know the status of a particular image, and for that you just visualize that image by using IMShow. IMShow, that is a part of the plotting library already included in our program, that is plt.imshow. Then plt.show will display the image in the screen, and this is the image displayed there. Then now, suppose we want to print the details regarding some of the images. We have to verify whether all the images are now available in our computer's memory. So for that, suppose we want to display some of the images, and for display the first 50 images of the data set with the help of, and for that we can make use of this particular code. I don't like to explain the various statements included in this code, and when that particular code is executed, we can we get an output like this, and this is actually a snapshot of the data set now loaded in our computer. Then next task, that is after loading the data and performing some pre-processing operations, pre-processing operations, and these are very important. Next task is to build the model, and building the model, and that is